So the next application of our 2D vectors is going to be something called projectile motion. And so this is going to then incorporate kinematics along with our 2D vector problem set. So the first thing we'll talk about is a ballistic trajectory. Now if you launch an object into the air, we call that the projectile. So the object that's actually flying through the air is the projectile. And then the path that it takes is referred to as the ballistic trajectory. Now we're assuming that gravity is the only force acting on it. So if it has, say, a motor or something like that, an airplane, that's going to be a little bit different. Now there will be air friction, of course, on anything that's flying through, but we're going to be ignoring that. And so we'll assume that the only force acting on it is the gravitational force. So obviously something gets it moving, but once it, say you kick the ball or something like that, but once it starts moving, we'll assume that's flying through the air and that only gravity is acting on it. So there are a couple of assumptions that we'll be making for that. If that's the case, then the net velocity vector will be a tangent to the path in each case. And so down here, again, tangent, remember, just means it's touching the line only in one place. So that would be this vector over here. At the very top of the path, the net vector is going to be just straight forward and then down, and again, just carrying down like this. So tangent to the path just means a line that just touches the curve in one place. So the net velocity vector then is going to be, or can be broken up into the horizontal and a vertical plane. So I have them tail to tail here a bit. We could draw them head to tail and make the triangle. So I have a horizontal component and a vertical component to there. Now the horizontal component is going to be uniform. That means, or because there's no horizontal forces. So we're ignoring air friction, so there's no force acting horizontally. And so that means this is going to be constant. And so regardless of where we are, this vector has to stay the same length. So from where we start down here, all the way even up to the top, and then all the way back down, this Vx is going to be the same because there are no horizontal forces. The only force we have is gravity. Now in the vertical direction, which would be then closing off the triangle, it's this line over here, it's going to be high at the bottom, and then as we go up, because it's decelerating as it goes up, it's getting smaller and smaller and smaller until it gets to the highest point where the vertical velocity actually reaches zero. That's the highest point where it changes direction. It comes to a stop, at least vertically. Now it still has all of its horizontal motion, but it loses its vertical motion. Once it hits there, then it starts accelerating downwards, and so we see then the vertical velocity vector growing as we come back down. At any given height then, those velocities will be equal and opposite. So just like we did when we threw an object straight up and it came back down, at equal heights, the velocity on the way up and the way down was the same, but just opposite in direction. And so if I look at an equal height here, this velocity vector here at the equal height should be the same length as this one, but opposite in direction. And then again, as it goes down, it gets longer. And then as you get to the top, the velocity vector in the vertical component at least gets smaller. Now, because gravity is the only force acting on it, the acceleration is equal still to this 9.81. Now, that's only though applying, of course, to the vertical plane because there's no acceleration in the horizontal plane. So we're going to look at two specific cases then of this. The first one is going to be then projectiles launched horizontally, and then we'll look at what happens when they're launched at an angle. So just with all of our vectors, keep in mind that we're going to keep our horizontal and vertical components completely independent of each other. And because they're independent of each other, that means I can treat them as two separate problems. Now, one thing that means then is that if I dropped an object straight down off of a table and I rolled another one off of that same table, they should hit the ground at exactly the same time. And the reason for that is the vertical components to those are going to be the same. So if I just drop an object, it accelerates as it moves downwards, and so higher up I have a relatively small velocity vector, but as you get closer to the ground, the velocity vector grows. Now if I shoot an object off the table like this, the same thing in the vertical component is going to happen. Now we do have this added horizontal component, but remember those are independent of each other, and so they shouldn't affect each other at all. So in terms of the downward motion, those two vectors should be the same, those two should be the same, those two should be the same, and at the end. And so the downwards motion is going to be exactly the same for objects going straight down and one following then this projectile path. Now that can be a little bit counterintuitive. You see the same thing with a firearm. If you're shooting a gun and you're shooting it horizontally, the bullet that you shoot out is going to go much further than something here, but the bullet that you shoot out would land at the same time as say if a shell casing popped out and hit the ground there. Because the falling motion is the same for both something that's going straight down or something with some horizontal motion. So they do land in a different place. So this one obviously will be further out from the table because it has that horizontal motion, but they're going to land at exactly the same time. Now the horizontal velocity vector, of course, is the same all the way through, and then that vertical one is growing all the way through. Now your initial speed in this, and this is something to watch with this, your Vx is 0 in that vertical plane up here, because all of the motion at the start is going to be horizontal. And so you have horizontal motion, but no vertical motion at the very, very point, or the highest point here, which is like the highest point in the trajectory. So when we solve these problems, what we're going to do is we're going to split our motion up into two pieces. We have a horizontal and a vertical component. The horizontal component is uniform motion, so we use our v equals d over t because there's no acceleration. Our vertical component is non-uniform, so there's acceleration, and so we'll use one of these four then to solve for those. And the variable that links the two is going to be time. The scalar doesn't really depend on direction, but again, as soon as this hits the ground, it's going to stop moving forward and moving down. And so time is the one then that's going to basically link those two components together. So let's look at a couple of examples of these. Now the general way we're going to approach this is we're going to look at the horizontal component and look at the variables there, look at the vertical component, look at the variables there, and whichever one that we have enough information to solve for time in, we'll typically solve for time there and then use that in the other component. And again, remember that time is what's going to link those two. So when you're doing these, I would recommend just starting with the variable list for both the x and the y component, and then looking to see which one you can start solving for time with. Now it's not always going to go that way, but that's a pretty good general way to start these questions. So this one here, we have a toy car rolling across a 95 centimeter high table. It's at a speed of 15 centimeters per second. The car is going to roll off the edge, and we want to know how far away from the table it's going to land. And so if we start with basically just the diagram, so we can look at our variable there. We have our car heading off of there, and when it goes off, it's going to follow this kind of projectile path until it hits the ground 95 centimeters below. So then we can put the legs there. And so what we want to do is we want to look at what some of our variables are. And we're going to split them up into our x component because we are going to have velocity vectors in both. And so we always want to be splitting those ones up when we're doing our variable list. The only thing that's the same between is going to be our time. So first of all, when we're looking at our x component, when I'm leaving the table, all of the velocity of this car is horizontal. That means that this 15 centimeters per second, that is going to be my horizontal velocity. And so my velocity in the x component is going to be 0.15 meters per second. Now because my acceleration in the y component is going to be meters per second squared, so that's just your g value, I am going to work these in meters and seconds. So for the rest of it there, I don't know how far from the table it's going to be. That's what I'm looking for. So I am going to need to solve for that horizontal distance. So my d, that's what I'm going to be looking for. And I also don't know what my time is, because I'm not given that in the question. So this one here, I don't have enough information to solve for time yet. But if I know what time is, then this d value is going to be easy to solve for. So we're going to go to our y component, and we'll see what variables we have there. Now we know that the table is 95 centimeters above the ground, and so that means then that the vertical height that it's going to be going is going to be then this 0.95 meters. Now what we need to do is we need to give a direction for these. For our x component, what we'll do is we'll just take the direction of motion as being positive, and then all of these will always be positive because the car is only going to be moving in that one direction. My vertical component, there will be up and down motion in some, but in here it's all going down, so it's going to make sense to make down my positive direction. And so then my distance in the y component then is going to be 0.95 meters. And so that gives me that distance. My acceleration will always be 9.81 in the y component. So that's always going to be a known value. That's just the g value. And remember that because all of my initial velocity is horizontal, that means the initial velocity here is actually going to be 0 meters per second. And whenever you're doing a horizontal launch, this is just one that you need to know is going to be 0, and that's true for all horizontally launched questions. And so what we're going to do then for here is we have enough information here that we can solve for the time. And once we solve for our time, then we can fairly easily solve for the overall distance and in the other component. So to solve for our time, we'll use then the d equals VIT plus 1/2 AT squared. Now this is going to be a fairly common question or equation to use for horizontal launch. It works out really nicely with that VI equaling 0, and so this is one that we typically use for these ones here whenever we can. And so then the distance is going to be equal to 1/2 AT squared. What I'm interested in here is the time, so I'll multiply the 2, divide the a, so it's going to give me 2d over a equals t squared. And then of course I can square root both sides to solve for t. And so we have 2 times that 0.95 all divided by 9.81. Scroll up here. That's going to equal t, and then if we put that all through, we'll get 0.44 seconds for our t value. Don't forget to square root that as well. Now we will use the whole number in our calculator, but we can round that off here just for what we're posting here. So then I'll take this t value. Again, time is going to be the same in both components, so we'll take this t value down here, and that's going to be the same as the t for the horizontal component, because that's how much time it's going to be in the air. And then, so in that case, in the horizontal component, I can take then the d of x must be equal then to just the velocity in x times the time. So velocity times time is going to be that distance. Again, velocity equals d over t is the one we're using for all of those. And so I can take the velocity, and all of the x velocity is that initial velocity, and that's going to be constant all the way through. So if 0.15 meters per second times at 0.44 seconds, and we'll see meters per second times seconds, I'm left with meters, and so then we'll get 0.066 0 meters. Now we have 3 significant digits, so we certainly could leave it there, or we could just go 6.0 or 6.60 centimeters, depending on what the question's asking for there. But certainly you could leave this one in meters, and you have the right number of significant digits, so there'd be nothing wrong with that either. So for this next, we have a cannonball being fired off of a cliff. It's leaving the cannon with a speed of 150 meters per second, and it lands 466 meters from the base of the cliff. And so this one here, we have a cliff, and then the ground below, and so the cannon is heading along some sort of trajectory like that. This distance here, this is the horizontal distance, so that's going to be my 466, and what we're looking for is how high is the cliff. And so for this one, now we're going to be looking for our vertical distance here. Our initial speed, again, all horizontal, so this will be horizontal launch. So all of that horizontal speed is going to be that 150, and the vertical speed initially is going to be 0. So then that's always going to be how these ones go for these horizontal launches. So in my x component then, I see that I have a d value, so it's that dx equaling to 466 meters. I have a velocity equal to 150 meters per second. And what we see here is that I don't know my time, but my time here I can solve for the x component. So in this case, we'll be solving for the x component first, we'll solve for the time there, and then we'll be able to use that in the y component to figure out then the height. So we can go right away and solve for the time here. And so I'm going from the equation d equals v over t. So just be careful rearranging this. The t is in the denominator, so we have to move it to the numerator first. So we get vt equals d. And then we can divide out the v. So we get t equals d over v. So just be really careful with that rearrangement. It's a fairly common one in these, but just make sure you're moving the t to the numerator before you isolate it. Once you have that, it's just 466 divided by 150. And so our time then for this one is going to end up being 3.106 seconds. And there's some more decimals after that, and we'll of course carry the whole number through our calculation. So then if we go to the y component, again, as always with the y component, the vi is going to be 0, and that's true for any horizontal launch. And that's just because, again, all of the initial velocity is horizontal. It hasn't started falling until it kind of goes over the side of the cliff there. The acceleration is also always going to be 9.81. Again, for these, I would recommend always taking down to be your positive direction, just because everything is going to be in that downwards direction there. So we don't have a lot else overall here, so we don't know the distance. Now we didn't know the time right out, but we do have the time from here, so we can use that time then, of course, as 3.106 seconds. And so what we'll do is we'll solve for the distance, and we'll use that same equation we used last time, and this is a very, very common one for these horizontal launches. It's a really good one to use, again, because that VIT term just drops out. And so I have d equals 1/2 AT squared. This one I don't even need to isolate anything because d is already isolated. So I get 1/2 times 9.81. But don't forget to square that t, 3.106. And it is a really common mistake to forget that squared there, so just be really, really careful with that. And so the distance that we're going to get then is 47.3 meters. Now the next one that we can ask then is what is the speed with which the cannonball hits the ground? And one thing that you really need to watch with this one here is that when the cannonball hits the ground, it's not coming straight down. It's going to be always coming at some angle here. And so that means I'm going to have both horizontal and vertical components then to that final velocity vector. So we can use this variable listing the same as we did. So we'll use these collection of variables here. But when the cannonball is hitting the ground, again, make sure you always remember that it's coming in at an angle. And so you always need to be worried about two components. So we're going to get then this vertical component. So I'll have that v, and this will be the final velocity in y. And then we'll have a horizontal component, which is coming in from here. Now the horizontal component's an easy one, because remember that the horizontal velocity doesn't change at any point along here. So this velocity of 150 was 150 at the top. It's still the horizontal velocity at the end. And so the vector down here, the vx is actually equal to that 150. And so that's not one that you're going to have to calculate. You'll really have that one always given in the question. The one we do need to calculate, though, is this vy. So we need to know what is the final velocity in the vertical component, and then we can combine that with this vx in the bottom, and then easily come up with the net velocity vector. Now we already have a few. We have the vi, we found the d and the t. And so what we can do is we can use the vi or vf squared equation to solve for this final velocity. Now that will give us the vertical component, and we do still need to then combine the two to get the net velocity vector, because don't forget, this is the one we're actually looking for, basically the speed on impact, which is a combination of this horizontal and vertical one. So let's solve for the final vertical one, and so my v final, so this is y component. So I have vf squared equals vi squared plus 2ad. Now again, don't forget, vi squared is equal to 0. So my vf squared, which is what I'm looking for, or vf, is just going to be equal to the square root of 2a and d. So my vf is equal to the square root of 2 times 9.81, that's in meters per second squared, and then times the 47.3. And again, we'll use the whole number from our calculator here. So when you put those values in, our vf value then, in the vertical plane then, is going to be 30.5 meters per second, or if we use the whole number, 30.476. A few more digits, and that'll be meters per second. So that now gives us our vertical velocity. But don't forget, we still need to combine that with the vx, which in this case turns out to be a much bigger part of the overall. That's 150 to 30, but both do matter for this one. So to come up with the velocity of the net force vector here, what I can do is I can just use Pythagoras' theorem, and so my v net squared is equal then to vy squared plus vx squared. And so my v net will be then equal to the square root of this vy squared, which is the 30.47 squared, and then plus the 150 squared. And when you solve for that, we'll get a v net of 153 meters per second. So a fairly common question when you're doing these ones here, to come up with the speed when it hits the ground. And this could be any object that flew off of a horizontal launch there. Just remember that's always landing at an angle, so you always have two components that you need to consider there when you're solving for those. Now this one as well, we were asked just for the speed. That's the scalar quantity, so we don't need any direction. If you were looking for direction, typically it's going to be the direction from the horizontal, and that of course you could get just using tan of vy over a vx.